Okay, so we're going to go ahead and get started back in with Melissa Emory, who's going to be taking us beyond endoscopy via Poisson.
Just setting a timer. Okay, thank you so much for coming, and thank you so much for coming to a talk on beyond endoscopy. And it's not a colonoscopy. I know it can sound concerning, but hopefully this will not be painful. But thank you very much for having the conference and for the organizers having me. So this is joint work with Malars Espinosa Lara, who is currently a postdoc of Jim Arthur at the University of Toronto, and Debanjana Kundu, who did her PhD at the University of Toronto. She started with Jim Arthur and then went to Kumar Murthy, but she's now at the University of Texas, Rio. I'm looking at Leo for the name, Rio Grand Valley, thank you. And then Tian'an Wang, who is a assistant professor at the University of Michigan Dearborn. So as you can tell, there's a lot of connection with the University of Toronto, and this started at an AIM workshop in 2017 with all of us. And for the Langlands program, it's kind of, some people would call it a grand unified theory. Some people don't like this term, but I do. But one of the key ideas is that you have, on one hand, you have representations of Galois groups, and on the other hand, you have automorphic L functions, and you should be able to relate these things. And basically, what Langlands did is instead of making an island of number theory bigger or harmonic analysis, what he did is he formed a bridge between the different areas of like algebraic geometry and number theory and harmonic analysis. And in particular, in the Langlands program, we typically use tools from harmonic analysis to prove difficult things in like representation theory or number theory. And what this is, beyond endoscopy, is a program. And the one that I'm going to talk about today is really the one envisioned by Langlands. So there are different paths, and Langlands and Jim Arthur and others would say that everyone needs to push these paths, and then whichever one works, that's fantastic, right? So, but what I'm going to be talking about today is really Langlands' vision, carried on by Arthur and now his postdocs and students and others. But the goal of this is to prove this thing called functoriality that we won't really get into, but it's this nice mapping from one thing to another, but to prove this conjecture and the analytic continuation of functional equations of all automorphic L functions. Another hope, and I put this on the slide just because Jim Arthur has told this to me a number of times, and I don't want to forget it, or for us in general to forget it. But there is a hope that once we get this thing of beyond endoscopy and functoriality, which it generalizes techniques of Taylor's and Wiles, it'll lead to a general analog of the Shimura-Taniyama-Bay conjecture and the analytic continuation and functional equation of all motivic L functions. So there is like we've just started this thing, and there's a lot of hope in what will come out of it, you know, down the road. So those people just finishing their PhD at, you know, 28, 29 years old, maybe in their lifetimes, right? Like that's the hope, maybe, right? Maybe. I suppose we're optimists, right? So the strategy about proving this principle of functoriality is basically, I just wanted to talk a little bit about these sides. So recall that the trace formula, it's an equality between two distributions. We have the geometric side and we have the spectral side. And on the geometric side, it's like a sum of the volume of gamma. Gamma here is running over the regular elliptic conjugate classes in G. And this volume refers to some adelic volume. And this O gamma F is an orbital integral associated to the test function F, and we'll talk more specifics later. So that's the one side. The other side is something called the spectral side. And here there's a main term where M of pi is the multiplicity of a representation pi. And then we have the trace of that. And again, F is some test function. And I should say M pi is the multiplicity of pi in the L2 discrete spectrum of G. So in any case, the point is you have two sides of the trace formula. You do some things and then you do some matching, right? So it's kind of like a puzzle. So if you like puzzles, this is kind of like a puzzle, right? Okay. And Langlands in this, he wanted to do this construction of something called a refined trace formula. So we have all these different kinds of trace formulas, right? We have the stable trace formula, the invariant trace formula, just many different ones of them. But this is a different trace formula that'll be utilized here, and we'll talk a little bit more about that. But in order to talk about this, I want to talk about, so if you just let G be any reductive group, and by if reductive, just a nice group, right? So if you're not sure what a word means, just think nice. It means nice, right? So think GLN if you like, or whatever. Let R be a representation of this thing called the Langlands of the L group. And this L group, what this is this is the dual of the group, semi-product of the Weil group. The Weil group you can think of as an absolute Galois group. So you should use the Weil group, but you can think of it as the absolute Galois group if you're not familiar with it. And if your group G is split, then this now is just the direct product, right? If it's not, then there's some action involved. But just for the moment, think things are split. And so what we really would care about in that very nice setting is the dual group, right? Now, when we talk about dual groups, and so this is the correspondence between you want to work on one group, it tells you something about the other group. And for G, well, for the general linear group, I mean, the dual group is just the complex points of the general linear group. That's nice. We all know what GLN is, right? For the special orthogonal groups, it's the symplectic group, okay? And you can go back the other way as well, right? And you have the special orthogonal groups. But here, this GSP2M, that means a similitude group. It just means you have this like factor, like a GL1 factor out front of it. Its dual group is G spin of 2M plus 1, right? And G spin, well, if you haven't seen my talks on G spin yet, it's a great group, but you don't really think of it as a general linear group or as a matrix group. And I won't divert this talk into that. But if you instead look at G spin, then the dual group is GSP2M, right? And why I mention this here is because we're talking about beyond endoscopy, right? But endoscopy, the first thing, if you have a group like SO2M and the dual group is SO2M, that's fine, right? You can go into another classical group. It's not so bad. But if you're looking at endoscopy, it doesn't work when you're looking at a group like GSP2M, because then you're going into the dual group of G spin 2M, 2M plus 1, but then you have the spin representations and complications. And so instead, if you work here and go this way, now you're back into something that you can embed into a general linear group easily. So, but that's endoscopy, is taking the L group of one group, right, of a smaller group into the L group of the other group. So for instance, if you had the L group of the special orthogonal group, that's going to embed nicely into the L group of GLN, right? Because SO goes into GLN, right? Good. And what beyond endoscopy does, it takes a little bit bigger of a group so that it doesn't go naturally into this thing. But it's much more complicated, and that's why we have this whole notion of beyond endoscopy. And what Langland's idea to tackle this was to weight the spectral side of the trace formula with this coefficient, this mu r of pi. So this is associated to this representation R, and this representation is in the L group of G, but you can think about it as just of one of the, like in some classical, a representation of some classical group, if you like. Right, so this is just that same part from before. And the idea is that this weight factor, this mu r of pi, it should not vanish if and only if this L function has a pole at z equals 1. And this is an automorphic L function. And in general, due to the presence of non-tempered representations, the only thing we need to this spectral side limit will not converge. And there's a limiting process in this thing. And so one of the first steps is to make things to where this limit will converge. And then one thing to note is that the only such non-tempered representations is the trivial one. In our specific case that we'll be talking about later. So what we're going to talk about in a little bit is GL2 over a number field. And work has been done of GL2 over the rationals. And if anybody here does representation theory, if you do something over the rationals, if you were as naive as we were as graduate students and postdocs, we thought extending something to a number field should be easy. this should be very doable, right? Like, okay, just idealize things and it should all be good. That was our, and I think that's why they give us as graduate students these problems, because we're naive, right? As it turns out, it's much more complicated, and more senior people are like, yeah, that would be hard. But Jim didn't tell us that. He's an optimist. In any case, what Langland showed, so work has been done on GL2Q, so we're going to talk about this for a couple of slides, and then we'll get into our work over a number of fields. But he showed that this thing here, this mu r of pi times the multiplicity of pi in the trace, that this equals this thing here, right? Where AP is the Satake parameter of pi at P. And if we assume the mean terms on both sides of the trace formula, right, then this guy here is the same as here, if we're assuming that. And so if we want to show that the for the limit to exist, the contribution of the non-tempered spectrum needs to be removed. So that's the problem. And that's why we isolate the non-tempered part, which in our case happens to be the trivial representation. So that's the whole goal of this 85-page paper, is to simply isolate the trivial representation. Good. So we have this equality from before. We can write this as this, and then what remains on the spectral side should now converge, because you should have a matching. This means that the geometric side should converge. And in Franklin, Langlands, and Go, this paper, they suggested that an additive Poisson summation type formula, it could be applied to the regular elliptic contribution on the geometric side and to cancel it. And what Ali Otug did for GL2 over the rationals is he did isolate this trivial representation, and he completed it, the full thing in three papers. But there are several choices to make. So in this work that we're going to talk today, it's just the very next baby step, right? So Langlands proposed this in 2004. Ali Otug did this in 2000, I think like 2010, or something like that, like a few years later. And his PhD advisors, I believe, were Langlands and Sarnak, but don't quote me on, I think that's who they were. In any case, but he took a step, right, a prominent step. And our step is just a little baby step. But so far, nothing else has been done, right? And there's much work to do. He chose a particular test function. You would need to choose different test functions to be in more generality. He chose the representation R to be the Kate symmetric power of the standard representation. And in general, you'd have to do all representations. But he did compute the limit in this case, and did the and said what the trace of the trivial representation is and isolated it. And he showed that this can be manipulated so that the right hand side of this equation converges. And this is really just, Ali's work was just a proof of concept, right, that this could be done. One thing to keep in mind is that the hypothetical Poisson summation formula, the leaders in the field know that this cannot literally be true, was a quote by James Arthur, or Jim Arthur, however you want to call his name. So in any case, but like I said before, this is the only example of the removal of the non-tempered spectrum via Poisson summation until our work. So again, the goal is to try to understand the shape of this new refined trace formula. Like, that's the goal. And again, we have the spectral side and the geometric side. And the goal is to find the value of the trace, the value of the trivial representation in this side and the geometric side. So to talk about our work, K is a number field. G is GL2 over K. Jim Arthur is working on GL3 over K. When I started at Toronto as a postdoc in 2018, he thought GLN would be very doable. As it turns out, GL3 is really hard. So the point is, you have many numbers to work on if you want to work on this kind of 3, 4, 5, 6, you know, keep going. But this is the test function that we use. And then this, given a regular elliptic element, gamma and GL2K, this is the characteristic polynomial, where tau is the trace and delta is the determinant of gamma, which generates this quadratic extension of L = K of gamma. And this gamma will show up throughout the talk. So, And then we fix immediately a prime ideal P of K, and then let Q be any ideal, any prime ideal. And then this is just reminding those of us that aren't that familiar with the trace formula, some nice things about orbital integrals, and that is that they're invariant under conjugation by gamma. And in particular, we get this thing here. And this is kind of important, and I should keep an eye on my time. Okay. But this, so this determinant of gamma, the norm is this here, and this K is important, and that has to do with an assumption that we have to make in our work, and that is that the order of your prime ideal P, so remember what the order of a prime ideal is, it just means it's, yeah. So we have to make this assumption that it doesn't divide, the order in the class does not divide the integer K that I just referenced. Because otherwise this thing vanishes and that's not what you want. So it's an assumption which is necessary. And the point of this is that you do a bunch of stuff, and I'm running out of time, so I'll kind of skim through this. You do a bunch of stuff to isolate the trace of the trivial representation. And I'm going to skip through some of these slides, or I'm never going to get through it. And in this work, we use Hecke L functions, and we also use the Zagier zeta function, which is kind of like an L function with a factor stuck in front of it. That's how I think of it. And we have to use the Zagier zeta function in order to work with the approximate functional equation to be able to utilize that. Yeah, and then we open up. So basically, we do. When you start with it, you determine the volume of the orbital integral. Those are calculations using the class number formula. You do the approximate functional equation, which is just techniques in analytic number theory, but it's like simply Ivaniak's book, like applying it to our case. You do Poisson summation, which you have to be careful in choosing a lattice. Like there's a lot of details in this, but it's classical, like doable. And then you do, you end up with these Kloosterman sums. Which are quite beautiful. And hopefully, I'm not seeing the slide that I want to get to. But in any case, you do the Poisson summation, you get these Kloosterman sums that you need to, hold on just a second, there you go. I was afraid I had deleted the wrong slide. But you do get these Kloosterman sums that you need to evaluate. And one of the most beautiful things, I don't know, to me in this, is that you end up, after doing Poisson summation, this is like a shortened version of it, of what you get. But you end up with these Kloosterman type sums that you then evaluate. And which in our land, like if you're proving, Saul Friedberg did prove the fundamental lemma for SL3 on doing something, and he also used Kloosterman sums. It's not that uncommon to get them. And in there is the Hilbert symbol. But in any case, the evaluation of these sums, they're complicated, but they are beautiful. But at the prime 2, they're a nightmare. But one of the things I like to show my Calc 2 students is that these are geometric series, finite geometric series and geometric series. And so I'm like, you say you never used, well, you can use them, right? They're beautiful. But what I like about this, and in particular, is that it's just, is that, hopefully I didn't just delete my mute. Anyway, but is that you end up factoring, doing some very complicated, just changing the orders and doing some geometric series, but it ends up factoring to this thing right here. But this equals that. So this whole thing is 0, right? So you get this monstrosity of things, and then you get it to equal 0 as it should. So any case, and what Jim Arthur would tell us is that when you see structure like that, pay attention because there's a reason for it. So then it's important to understand the reason. We don't understand the reason of why these things work out so nicely quite yet, but that's where we're at. And that gives you beautiful things of a quotient of zeta functions that we end up utilizing in the work. So, and then you unpack things, fold things, and you end up getting what the trace of the trivial representation is. With that, I will say thank you.
Don't just have to separate the trivial representation, but there is more things appearing and separate them.
That is my understanding, but one of the first things you start off on is this formula that Langlands showed in his Beyond Endoscopy paper of the orbital integrals is this like 1 over, in our case, the norm of something equals the sum of these a series. And it's a starting space, and we don't have that. I don't believe in general. And I think, and Jim did that for GL3. It was much more complicated than he anticipated, thinking that it would be much easier than what it was, and it wasn't. So even just the starting space, but yeah. But I haven't worked on it, so I don't know. Yeah. Yes. No, I mean, we do not need it. No, yeah, not yet. But this is step 1. So then we have to compute the limit in paper 2 and then do step 2 in paper 3. So step 1. It's great. It's fun. Good.
Do your calculus students ever actually find those Poisson sums compelling? The reason for the series?
That's a good question. They smile at me,
Yeah.
but I don't know what that, I don't know. But and that you factor and things turn to 0, right? Like factoring in geometric sums, like that should be fun.
Go ahead, thank you once again.